Most of our energy comes from fossil fuels. We're familiar with gasoline, for example, to power our cars, but also we burn coal, natural gas to produce much of the electricity that we use. So what actually is a fossil fuel anyway? Well, fossil fuels are stored chemical potential energy. That means that it's internal energy in the material of a substance, but it's not due to the temperature of that substance. It's due to the arrangement of the atoms and molecules and how the electrons are shared and holding together those atoms and molecules. And they're holding them together like a compressed spring. And a spring is stored potential elastic energy. Uh, Different molecules can have stored chemical potential energy, and that stored energy can be released through chemical reactions, and they're released through a reaction with oxygen, which is a very reactive molecule that breaks apart those bonds and forms new bonds that don't require as much energy. And so some of that stored energy then gets released and transmitted into the kinetic energy of the individual molecules that we're chemically reacting. That's what combustion or burning is. Our bodies do it with food on a molecule by molecule basis, but if you light a fire of anything combustible or we burn coal or oil or gasoline, we're doing it more rapidly on, of course, it's always a molecular reaction, but we're doing it with lots of them all at once in a small space. And we can then generate a lot of heat, a lot of thermal energy, really just the kinetic energy of those molecules that we're burning. So where do those fossil fuels come from? They come from fossils. That means the compressed, highly processed over time remains of dead organisms. And the way that uh, ends up producing energy is, as I said, food has energy and you can eat that food, and then that stored chemical potential energy is in you. And then if you die, there's still that stored chemical potential energy, and through the passage of time and application of pressure by burying these things, you can concentrate that stored chemical potential energy into what it becomes, things like coal. Most of that stored chemical potential energy is not actually coming from animals or dinosaurs or anything like that, but from plant life. And the plant life uh, got its energy originally from the sun. So this chart is showing different amounts of stored potential energy per kilogram, different kinds of coal. They're all about the same. You don't need to memorize that. And we've already looked at this chart from chapter 3 that shows that all of the different fossil fuels, coal, oil, natural gas, they all have pretty much the same amount of energy per kilogram. And if we put butter up there, if you take a look at the Sustainable Energy book, see that food has a comparable energy density. It's all stored chemical potential energy. Uh, but how did that those things, how did plants get that chemical potential energy in the first place? Where did that energy start? It started with the sun. Sunlight provided the energy to drive chemical reactions, and the raw chemicals for those reactions came from water, carbon dioxide in the atmosphere, and other atoms and molecules pulled up from water or from soil to create those scrunched up springs of atoms and molecules in organic life forms. And so the energy source originally to create that stored chemical potential energy is the sun. When those organisms die and are buried, there's additional chemical transformation that can take place with the application of pressure and high temperatures underground over time that ends up giving you a more sort of pure or concentrated form of that stored chemical potential energy in the fossil fuels. And then we just do a back reaction. We liberate that energy back by sort of reversing the chemical reaction that took place in the first place. We oxidize it, that releases CO2, goes back out into the atmosphere. That's unavoidable. These fuels are sometimes called hydrocarbons because they've got a lot of hydrogen and carbon in the molecules that are storing the chemical potential energy. When you react oxygen with hydrocarbons, you produce oxygenated carbon and oxygenated hydrogen, also known as carbon dioxide and water, also carbon monoxide, CO. So it's inevitable that you produce carbon dioxide when you burn a fossil fuel. There is no way to burn a fossil fuel without liberating carbon dioxide. If you're not producing carbon dioxide, you're not burning it, so you're not getting that stored chemical potential energy. It's going to come out. So that's inevitable. The other thing to note is that it took hundreds of millions of years of this sunlight trickling down from the sun, and tiny fraction of that, I should say sunlight trickling down, sunlight energy gushing down from the sun, but a tiny fraction of that solar energy being used by plants to create stored chemical potential energy in the stuff of the plants, and then getting concentrated over the course of tens and hundreds of millions of years. So it's an accumulation of hundreds of millions of years of energy flow into a fuel. We started burning these things in earnest a couple of hundred years ago. So a million, and we're going to burn it all in the order of a few hundred years. So we're burning it roughly a million times faster than it was created. And that's why you had a million times slower process of pulling CO2 out of the environment to store these fossil fuels, and a million times faster than reintroduction of that carbon back into the atmosphere with the combustion of them. This slide shows that oil and natural gas frequently are found together, and there are various technologies to get those fossil fuels. Primarily, it's oil, coal, and natural gas, a solid, a liquid, and a gas form of these things. And then we can process the oil to form various different kinds of end products that we're more familiar with. We typically are not familiar with oil in our everyday lives except for lubrication of engines, but when we go to a gas station, it's gasoline that we're buying. And gasoline is a product of oil or petroleum that comes from a refinery. And in a refinery, the raw crude oil that is taken out of the ground is heated up to high temperatures and it evaporates, and we tap into that column, this distillation column of evaporated oil hydrocarbons, and pull out the evaporated material at different temperatures. And depending on the temperature that we're pulling that stuff out, then we let it cool. When it cools, it condenses back into a liquid. That's our different grades of gasoline or petroleum products. So gasoline, what we use in automobiles, for example, is coming out of the top of that distillation column. Diesel oil is coming out at a different level and has a slightly different chemical makeup, which has different properties in terms of how we can use it in our machinery. Again, that's just a review of our same thing showing us in our fossil fuels. We've got on the order of, say, 30 to 50 megajoules per kilogram of stored chemical potential energy. And then finally, over time, our consumption worldwide of fossil fuels has grown from about a little less than 2 gigatons oil equivalent. That means if we converted all of it to like the coal and the natural gas to how much oil would that be equivalent? And again, we remember from this slide that coal and oil, the numbers aren't too different, 29, 43, natural gas is 55. But anyhow, we take those differences into account, and this graph is showing that amount in terms of equivalent in terms of tons of oil. In 1950, worldwide, a little bit less than 2 gigatons, and in 2010, more than 10 gigatons. So a factor of 5 increase in 60 years. And uh, there's been a greater relative increase in that growth in natural gas, especially even in the years that are not included in this chart. And that's due to the items that are highlighted on the bottom of this slide, that it has become more economical to get natural gas. And natural gas does have the advantage, as we see on this slide, that it does actually have a higher energy density, more energy per kilogram than coal does, 55 million joules compared to 29 million joules. And when natural gas is burned, it produces less of the other harmful environmental pollutants than coal does, and it produces less CO2 per joule of energy that we get out. So it's a more efficient and cleaner form to burn. Of course, the extraction of natural gas, just as with the extraction of any of the fossil fuels, involves its own environmental issues. So, for example, fracking involves injecting chemicals into the ground to force the gas out, and those chemicals are then in the ground and can pose their own environmental consequences. Uh, this website uh, can help you identify where most oil consumption is occurring per capita, uh, and obviously varies around the world. Um, but that's your overview of fossil fuels.